Well, I share the distinction of probably being the oldest person in this room. I'm in my ninth decade. My father lived to 100, so I hope to come back again.
You don't look that old,
Yes, never judge a book by its cover. Now, we've come here to celebrate Rosemary's career, and we've seen her work, and I've singled out two of her important papers there. I also touch a bit on personal matters. For example, you'll see a picture of her, which we haven't seen today, and a B.1958 is the year she appeared on the planet. I think that's correct. And that, extraordinary enough, with her long Monash connection, is how long when Monash was founded by government. And although I didn't appear, I wasn't in the Olympic Games, and if I was, I would have been in the low jump, and I would have got a silver medal. Yes, it's a very nice one, but it's got 1958 on it.
Oh wow!
Yeah, that's when Monash was founded. Yes, the low jump is about where I am. Yeah, so that's important. So what I wanted to do to somehow integrate Rosemary's work and with what I've been doing and show there's a connection in the dynamical area. And so those are two of Rosemary's very important papers, and we talked about her tidal capture today and those two orbits coming together and then being captured, and we'll come to that shortly. And that's the other very important paper she wrote. So my career started off pretty well around with the Voyager project. I went to NASA as an associate in 1980. 1979 was when this craft, Voyager 1, arrived to Jupiter. And I think Rosemary reminded, she did her linear algebra course with me then. And, but it was launched back at 77 when she started at Monash, or was close there too. So that was a Voyager picture. But of course, the spacecrafts have improved and the cameras, and of course, we ought to thank Stephen Morton for his monumental contributions over the year. Many of my presentations wouldn't happen without Stephen's help. The Cassini took a much better picture, and now you're starting to see some of the moons. They're scattered across there. The small icy moons with, I think, probably Rhea off to the far right, and there's even a small one just lurking. You can just see a small guy just lurking, or maybe that's a part of the ring. So it's a beautiful system, and I think we can look on Rosemary and her as a sort of jewel herself. Saturn is sometimes considered as the jewel of the solar system, so there's a bit of parallel there. But there's Titan. It's a monster, and you can see the Encke gap there. And I think, someone mentioned Daphnis this morning, not one of the moons. I think Pan and Daphnis are co-orbital moons in that Encke gap, and they swap orbits, and that's another interesting thing here. But Titan is so huge, it stands out alone. It can't, and I realized a long time ago that it can't be a natural satellite. It's too large compared to the others. And back in 1980, I made this prediction. It was a captured moon. It's not a native. But what was the basis for that prediction? It all stems from this, what I call the Laplace's hypothesis, which was put forward about over 200 years ago, and that the planets had formed from the sun when it was once an infant cloud, contracting inwards and shedding gas rings, and planets formed then condensed individually from each of these rings. Laplace's theory was eventually discarded because if the sun had originally become rotationally unstable at such a great distance as Neptune, it could not have possibly contracted inwards to its present size without losing all its mass. Yet the planetary system's mass is only 1,000th of the sun. So that was a problem, and Sir James Jeans and Eddington, many others, realized that at the start of the last century. Good to see no way around it. But I was lucky enough to go to Oxford in 1967, and in fact I'm going back again in 2 weeks' time. My college has invited me there, Wolfson. I was their very first student, and they're quite keen for me to reappear after such a long time. Many of the greybeards have gone from then, and I've become the replacement greybeard. So that's quite exciting.
They have to come back.
Yes, there we are. Now let me continue onwards. I'm going to, yes, I could almost draw Alex into the picture, but I think, oh, he's over there. I hope you look as if you're fainting. The feature of the Laplace's model, it explained the circularity of the orbits and the coplanarity, but there were other difficulties as well. Why would a cloud shed gas rings? That's another story, and I won't go into that today, but it's all tied up with supersonic turbulence. And this is, I got a student in the computer science department, as was then Brian Hanley. He modeled these gas rings. This is a view of them side on. The real nice thing about the gas rings is they have a natural capacity to focus the condensates in each ring onto a well-defined circular orbit. So you reduce the accretional problem from a two-dimensional one down to one dimension. As long as the gas ring, which is in a state of differential shear, remains intact, you get a concentration of that. And Kerry Hurigan, one of my PhD students, showed that these particles would draw together under their self-gravity, and you'd get a major aggregation there. That's the idea. That was first put forward to the Australian Academy of Sciences in 1973. And so getting back to why Titan's so big, the masses of the gas rings bear a fixed ratio. If they do bear a fixed ratio to the mass of the primary, and F is the moment of inertia factor, the contracting cloud will shed a system of rings that are geometrically spaced. And more importantly, if you, in the case of the Sun, for example, which is about 300,000 Earth masses, if you have a ring of 1,000 Earth masses and F was 0.01, you recover Bode's law, but it implies the gas ring shed by Uranus and Neptune were the same, and 1,000 Earth masses, and such a ring contains 1.5% of its mass are rocks and ices, and that in fact are the masses of the planets Uranus and Neptune, which are thought to consist mostly of rocks and ices. So there was a sort of a physical coming together with the basic facts of the solar system, even though there were many unexplained factors. And so that's what led me to believe, when I applied that formula to Saturn, Rhea's mass and Iapetus came out naturally from that Tetius-Bode law, but Titan was 60 times too big. That led me to believe it was captured. And that's where Rosemary comes into the picture, because she has studied this capture process. And so what I want to do for the remaining part of the talk is to show what would the dynamics whereby Titan may have been captured. Iapetus today lives a long way out, more or less about 60 radii out, but I believe Iapetus was a cousin of Rhea, and it got somehow caught up with Titan and scurried out. But these fellows here, particularly Hyperion, I think it's a remnant of a destroyed moon, and this one's gone altogether. That's the picture that I put forward in 2006. Titan itself condensed in a solar orbit, and it consists only of rock and water ice. It does not, even though we know it has an atmosphere of nitrogen and methane, it did not acquire those. So that was a process against my model. Titan should have only consisted of rock and ice, and we'll come to that shortly. And so, but if it did start out there, let's see what would happen. It would come roaring into the system, possibly on a parabolic orbit. And we do know that the Cassini orbiter was slowed down from a parabolic orbit into a captured orbit. It had these thruster jets that sort of fired in the opposite direction, and it slowed it down sufficiently to come into orbit. And I believe that's exactly what happened with Titan. So this is where I draw upon Rosemary's work, her beautiful lectures that many of her former students have expounded today. And it was wonderful to hear those personal attributes that have been made to you, Rosemary. You really deserve the title of being a gem. Now, so I believe that Titan did come in, and at that stage, the initial Saturn system contained 3 extra moons. There was Iapetus, which I think was at 12, another moon that's lost, and then Hyperion, which I think is a remnant of that other moon. It came in on a parabolic orbit, and now this is where I use Rosemary's beautiful equations, really nicely drawn out, easy to read, and on the two-body problem. And we reduce it to a simple harmonic motion equation with the inverse radius, and then we finally come up with a solution for the orbit. And that's the one I've used in my model. You can see here, I've computed what the parabolic orbit of Titan would be as it came in, assuming that that Titan today has much the same orbital angular momentum as it did in the beginning. It may have crashed into some smaller objects, but these smaller objects, for example, Iapetus is only about a 75th of the mass of Saturn. So Titan may have lost some angular momentum, but not much. It more or less preserved it, and it's quite safe for us to assume up here that the specific angular momentum, h, remains roughly constant. M is the mass of the planet. And it's fair to treat it as a two-body problem, because you see Saturn Titan is so much smaller than Saturn. So we're just looking at, we're just treating Titan as a massless particle. So this is the final graphic that I came up with. You see Titan coming in on the top left on a parabolic orbit. It comes in perilously close to where Iapetus was, and I predicted this long before I did this thing. This graphic was produced over the last few days, and I would not have achieved it without the help of Stephen Morton, who's here today. He's also another unsaluted hero. So that's extraordinary at Rosemary. I think Titan came right by and sort of flirted, I guess would be the right expression, with Iapetus, and maybe dragged it right out to where it is today, way out at 59. But on the earlier orbits, these are sort of tangential orbits, but the outer two rings are where Titan came in, and it would have done many loops, eventually almost certainly crashing in to these others. And I think those other two moons were destroyed. And there's Hyperion. You can see it's a remnant of a moon. And there's Iapetus. And I think Iapetus may have got spun up when it was captured. You can see this ridge here. And initially there was a lot of heat inside, and the whole moon, even liquid water and liquid ammonia, because in my computational graphic, Iapetus and Rhea contain lots of ammonia and nitrogen. And so I think that's where Titan's atmosphere came from. There was that earlier graphic I showed you where Iapetus and Rhea formed in below the condensation lines of ammonia and methane. So Titan's atmosphere is not of its own. Titan came in as a rock water ice body. These other moons ploughed in, and the Cassini orbiter found there is a gravitational anomaly, X Xanadu, I think it is, and there's evidence that there's something stuck down there, and I think it's one of those lost moons. So that's there's the chemistry there. So what happened? Titan came in and crashed. Rhea was spared, but these other two, which were loaded with ammonia ice and methane ice, they then formed those sublimation of those ices formed the atmosphere of today. So the last clincher is that I believe that Titan, if my model is right, Titan, if it did form in a solar orbit, if it did form in a solar orbit, it would have been an oblate spheroid, not a prolate object as a natural moon. And in fact, that was found that Titan is slightly oblate. It originally came in quite oblate, but then over the years it's been tamed. Today is in approximate hydrostatic equilibrium as a triaxial ellipsoid, and it has been tamed by Saturn. It's lost pretty well all of its eccentricity, as we saw, and now it's also lost its original oblateness, but it still retains a little. So that's the end of my story. I just wanted to congratulate Rosemary on her career, and it's nice that at the very end of it our paths have sort of coincided. Thank you.